Hey everybody, this is video 44. It's our last video of the year. We've covered two periodic trends, atomic radius and electronegativity, and we're going to talk about the third one now, ionization energy. So, in the simplest terms, ionization energy is the amount of energy it takes to remove the most loosely held electron in an atom. And so it's the electron that the nucleus has less control of. And that's usually going to be, not usually, it's going to be a valence electron. I mean, take a look at this smaller atom. It's this electron here that's the one that's going to be easiest to remove. If there was an electron in here closer to the nucleus, it would be harder to get rid of. Same reasoning over here. This outer electron is going to be a lot harder to remove than something in here. And so I guess from this you could also draw the conclusion that, wow, I guess with this kind of atom with all this shielding, it's going to be a lot easier to remove that electron. It's not going to be held nearly as tightly by the nucleus as, say, the electron here. And you would be right, and that's the next slide. So yeah, smaller atoms that have fewer energy levels, which mean less shielding, will have higher ionization energies than larger atoms that have more shielding. So basically it's saying that small atoms, it's harder to remove an electron than it is for a large atom. And take a look here. Here is group 1. These are the alkali metals, at least from lithium down to cesium. That's about 5 of them, and you can see as we go down the group that ionization energies go down as the atoms get larger. Remember, lithium is the smallest one, and as we go down we just keep adding energy levels with each valence. Like lithium's valence electron configuration is 2s1, sodium's is 3s1, potassium's is 4s1. As we add an energy level, it becomes easier and easier to remove that outer electron because of all the shielding. See how the ionization energies decrease. Or another way to look at it is ionization energy increases as we go up. Now, going across a period, ionization energy, the trend is for it to increase. So going left to right across the period, it becomes harder to remove an electron from an atom. But take a look at the second period here. We can see that this increase occurs in an inconsistent way. For example, by the way, all these numbers are in kilojoules per mole. And so lithium takes 520 kilojoules per mole to remove its most loosely held electron. Moving right across the period, beryllium, it takes an increase, 900, but then for boron it drops down. And then as we keep moving right, ionization energy increases with carbon, increases in nitrogen. Okay, we're seeing an increased trend here. And then with oxygen it drops back down again before it finally finishes up with fluorine and neon being higher. So looking down here at this diagram, I've got kind of a visual on what's going on with that second period. You can see lithium, it goes up, it hits beryllium, drops back down to boron. Then it goes up on the way to nitrogen, then drops back down to oxygen, and then finishes up. And we can see that same kind of pattern being repeated in the third period from sodium to argon. So this is something that is consistent across all the periods. So why does it not increase steadily? You know, what's the deal as we move across the period? Why does ionization energy vary so much? So I've tried as best as I could to show the valence electron configuration, the orbital diagrams, well, both really, as we go across the period, to explain why we have that inconsistency in ionization energy. It goes up, then it goes back down, and it goes up, and it goes back down. So we'll start over here with lithium. Notice it's got one electron in the 2s. Well, its ionization energy is pretty low. In other words, it wants to lose this electron. It's easy to remove that electron because if it loses it, it has a noble gas configuration. Helium is the element right before it with 1s2. and so lithium's ionization energy is pretty low. Beryllium's, on the other hand, increases a good bit because, hey, we got a full 2s orbital. That counts for some stability there with that full 2s orbital. So it's kind of hard to remove an electron from this. But we go and add an electron, like with boron, and that's a 2p electron. If it lost that, it would have a full 2s, which is more stable than a single electron in 2p, and so the ionization energy will drop for boron. Then we see an increase for carbon as we get close to a 2p full 2p sublevel, or at least one electron in each orbital, and we get that with nitrogen. That's stable. Notice there's no pairs here, there's no repulsion, but in oxygen we add an electron and we get repulsion here, and that makes it easy to remove one of those electrons because it lowers the energy state. Then it picks right back up with fluorine, and then neon, of course, with the highest ionization energy. So the point of all this is that it can, how difficult it is to remove an electron from an atom depends on the electron arrangement, and it occurs inconsistently as we move right across a period. And then the last thing we're going to talk about is something called first, second, third ionization energies. What we've been talking about is the first ionization energy, and that's the amount of energy it takes to remove the most loosely held electron in an atom. But there are other ionization energies. For example, the second ionization energy is how much energy it takes to remove the second most loosely held electron. The third ionization energy, amount of energy required to remove the third most loosely held electron. And yes, there is a fourth. You can just keep going for as many electrons as you have. Well, let me just start off by saying that every time you remove an electron from an atom, you create a positive ion, or it becomes more positive, and therefore it makes it harder to remove the next electron. So each successive ionization energy becomes more and more difficult, requires more and more energy to remove an electron. So as an example of this, let's look at the first, second, third, and fourth ionization energies for aluminum. So I've got the valence electron configuration down here, orbital diagram, 3s2, 3p1. So to remove this electron right here, it takes that much energy, 578 kilojoules. But to remove the next electron, it jumps up pretty good. I mean, it jumps up a good, what is that? 1,300 kilojoules per mole almost. And that's because now you're removing an electron from a full 3s sublevel, and that's difficult to do. And then to remove the next electron requires that much energy. So there's a small increase, but whoa, I didn't show the next electron, but whatever it is, look at that huge increase between that one and that one. That's the biggest increase between any two. The reason is because at that point, let's take a look at the full electron configuration for aluminum. We're talking about after we remove these first three electrons, so that means get rid of these three, look what we have. We have a noble gas configuration. So we're talking about trying to remove an electron from this full 2p6, and that's going to be really, really hard to do, thus the big increase in energy. So sometimes you can tell by ionization energies what group actually the element belongs to. Let's take a look at the next one. So here we've got magnesium's first three ionization energies. So I've got its electron configuration written here. And so to remove the first most loosely held electron, that would be one of these three S's, it takes that much energy. To remove the second 3s electron, it takes that much, and then all of a sudden there's this huge increase between the second and third ionization energies. So we're talking now about removing one of these 2p6s, which as you can see is, again, neon, a noble gas configuration. So whenever you see these huge bumps between ionization energies, that lets you know that you're at the point where you're trying to remove an electron from a noble gas, and there's going to be a huge amount of energy associated with that. All right, Thanks for watching this one and all the videos all year. Appreciate your patience. See ya.